Hi, everybody. My name is Deepa Krishnaswamy, and today I will be talking about integration of deep learning algorithms for the lung segmentation and body part-specific anatomical classification with the Medical Imaging and Data Resource Center, or MIDRC. So to give a little bit of background, the Medical Imaging and Data Resource Center, or MIDRC, aims to build an AI-ready data commons to support COVID imaging research. Unfortunately, the data that's collected by this repository lacks critical metadata that's then needed to build cohorts and to facilitate data discovery, as well as obtain annotations of regions of interest. Unfortunately, assignment of the body parts that are included in images are often removed from the process of image de-identification, or they're not sufficiently precise, or they don't exist at all. So our main objective is to present an evaluation of a tool for automated anatomy classification on the MIDRC data. We also perform automated segmentation of the lungs, and we use shaped features extracted from radiomics to support the detection of misclassified and incorrectly segmented data. So I'll begin by talking about our methods and how we selected the series for analysis. So first, if we go to the MIDRC website, this is where we actually downloaded all of the data of interest. Now, once we've downloaded the data, we then ingested these into DICOM data stores, which are part of the Google Cloud Platform. We then extracted the DICOM metadata into BigQuery, and we used SQL to filter the data according to the DICOM metadata present. The criteria that we selected these series are as follows. For instance, we wanted to make sure that we had a consistent orientation of slices and consistent in-plane resolution. We also wanted to make sure there was no overlap of slices and that we had consistent spacing between adjacent slices. We also wanted to disregard any scout or localizer scans and only include series that had greater than 100 slices and also had slice thickness values greater than 1.5 millimeters and less than 3 millimeters. If we go to our GitHub repository, which you can access by the QR code at the bottom left of the poster, here we have the query that we actually wrote in SQL to do this series analysis. Let's go back to the poster, and here we can see the distributions of data that resulted from the queries, as seen here. Here we can see distributions related to the slice thickness, the patient age, patient weight, and the number of instances in each series. Now, once we formed our series, we then performed body part prediction. This is a method or BPR. This is a method that was developed by Sarah Schuhager of DKFC, and this was applied to predict the location of several organ and bone landmarks for every single CT volume. This method was also then used to annotate the different body part regions. This included regions such as the head, the shoulder and neck, chest, abdomen, pelvis, and legs. One advantage of this method is that we can actually label every single axial slice with multiple regions. Once we performed this, we then did lung segmentation and extracted radiomics features. For the lung segmentation, we used the method LungMask, where we performed segmentation of the left and right lungs. We then extracted 3D shaped features using the PyRadiomics package. And the reason that we wanted to do this was because it's very difficult to assess if the segmentations of the left and right lungs are correct over a large number of series. Therefore, by doing this sort of analysis, we could hopefully identify any potential outliers in the data. And as I mentioned before, all of our analysis was performed at the GitHub link that I showed previously, and we used Google Collaboratory notebooks. We also saved all of our output as standard DICOM segmentation objects and TID 1500 DICOM structured reports. Now let's go into some of the results. So after we performed the SQL selection query and we did all the analysis, this resulted in a final number of 369 series. So first, let's talk a little bit about the landmark analysis that we performed. So the body part regression method, or BPR method, produces a slice score for every axial slice. These values are then mapped to specific anatomical landmarks. So across a set of patients, the same score should actually result in similarly positioned slices. So as we can see here, a value of 45 represents the bottom of the lung, and a value of 75 represents the top of the lung. And in the axial images shown on the right-hand side, we can see that this is in fact correct. The images that are in the same row look anatomically similar to each other. We then performed an analysis of the various regions that were also produced by the body part regression method. So for each series and regions, we can plot the percentage of axial slices that are assigned to that region. Now let's go to some plots so I can explain this a little bit more. So here we can see the same plot that I showed on the poster, where for every single body part region, we can see the percentage of slices that are assigned to it. So for instance, since all these patients were scanned, had their lungs scanned, we can see that the ratio is very high for the chest region. This makes sense. But then if we look at other regions such as the head or the pelvis, we expect that not many slices would be assigned to these regions. But we can actually see that some patients, such as for this one, had a large ratio of slices assigned to the head. So if we click on this point, we can then open up the associated OHIF viewer, which connects to our DICOM data store, where we stored all of our segmentation and DICOM structured report results. So now if we open this, we can then scroll through the slices to see that actually, in fact, the head does appear in a majority of the slices here. So this is likely an outlier. We can also see the segmentations that we performed automatically of the lung, as shown here, and the body part regions and landmarks on the left-hand side for every single axial slice. Another part that we can analyze, if we go back to the poster, is to perform an outlier analysis using radiomics. So as I said before, to assist in detecting incorrect segmentation results, we analyze different 3D features, such as sphericity, elongation, flatness, and measurements of the axis of the segments corresponding to left and right lung produced by lung mask. So let's go back again to our plots. So this is an example of looking at the flatness, one of the features. And here we have two box plots for the right and the left lung. Now, we expect that the distributions of the flatness would probably be similar between the two sides of the lung, but we can see that they are not. So if we click on this particular point to assess some of the outliers, this opens up this OHIF viewer link. And now if we scroll through, we can actually see that there might have been an issue with segmenting the lung here. Now let's go back to the poster. Another way that we can analyze some of our data is by using a Data Studio dashboard. So a Google Data Studio dashboard was created to display data statistics and to also help identify resulting artifacts in an easy and interactive manner. So you can check out the dashboard yourself here at this QR code. And here I'll open it up. So here on the first page, we have a summary of the data set. Here you can look at the different collection IDs that were analyzed, patient sex, and the number of instances. We can also filter by many different categories, such as pixel spacing, slice thickness, etc. The plots are automatically updated when we select any particular value. We also created pages for the other types of features analysis. So for instance, if we look at the radiomics features, we can choose which region we first want to analyze, so the left or the right lung. We can then choose a specific shape feature that we would like to learn more about. So for instance, let's choose sphericity. Once we choose this, the histogram on the right is automatically updated, and this provides us with the number of series instance UIDs that correspond to every single value on the x-axis. We can then scroll down and we can actually open up an OHIF viewer link, as I showed previously, to view these particular series. For the regions analysis, we can also choose a particular region that we want to analyze. So let's choose the chest. Once we do this, our box plot is updated on the right-hand side. Sorry, our histogram is updated on the right-hand side, and this shows us the number of series that were assigned to that particular region. Again, we have the OHIF viewer links that you can view. Lastly, for our landmark analysis, we can pick specific landmarks that we would like to look at, and we can get the number of series instance UIDs for every single landmark. Now if we go back to our poster. So hopefully I've given you a good idea of the types of analysis that we have performed. Our future work includes the application of these AI tools to larger cohorts and their deployment into the MIDRC portal. And hopefully I've showed you that we have developed tools for data curation and classification that will be implemented in the MIDRC repository. Thank you.